All right, so I think we had everybody come in now. I want to take this time and thank everybody for attending this Cloud Computing and Workflow with Rescale webinar. It looks like we have a few people that we know and a few people that we don't know. For those of you that we don't know, I'm going to go through a brief overview of the Converge product family and the shifting paradigm toward a predictive CFD. Followed by Ilea Graedel of Rescale, detailing the current and projected HPC and cloud environment for engineering applications. And from there, we'll show a brief case setup in Studio, Converge Studio, of the SI8 tutorial, and then we'll hand off to Mulyanto Poort for an in-depth demo of the Rescale environment. I guess I'll start by introducing myself. My name is Rob Kaczmarek. I'm the Director of Sales and Marketing here at Convergent Science. And from there we can kind of get started. So as many of you know, Converge is known for the work done within the automotive industry, and I guess more specifically within the internal combustion engine realm. As of a few years ago, we began to branch out into these new industries, and we've made some really great headway and friendships along the way. As you can see from this slide, the new industries include gas turbines, aerospace, electronics, biomedical, and marine, just to name a few. So as many of you know, Converge is a fairly unique CFD package in that we automate and fully couple our mesh with our CFD solver. We will dive into that kind of in the next slide a little bit deeper. But with that being said, this approach allows us to adaptively refine the mesh during runtime, a feature that we call AMR, Adaptive Mesh Refinement. We also have a detailed chemistry solver equipped with dynamic mechanism reduction, or DMR technology, that will reduce simulation time for detailed chemistry cases. We also have advanced submodels that we will touch on a little bit, but we won't go into great detail on these, and I'd encourage anyone with any questions about those models to contact us for more details, and we can kind of give you the details you'd like. So as I mentioned, Converge is unique in that we completely remove the meshing up front and we automate it at runtime. So this streamlines the workflow that you see with Converge. And as you can see from this graphic, we have a simple three-step process with the meshing done automatically at runtime. So Converge uses this automated, fully coupled structured orthogonal Cartesian mesh that is cut fit to represent the geometry exactly. We also offer AMR, on-the-fly grid scaling, and handling complex geometries and moving geometries is just as easy as non-moving for us. The benefits we see from this, aside from the obvious of not spending the time creating a mesh up front, is that we can remove the user-to-user variations along with handling incredibly complex geometries easily. This combined with refining our mesh at runtime, utilizing our AMR technology, as you can imagine, increases the efficiency and accuracy of the results as well. So for those of you not familiar with the adaptive mesh refinement, what this is an approach that adds cells when and where they're needed at runtime based upon user-defined parameters or gradients. The user can specify one or more gradients to refine against and then specify how many levels of refinement they'd like to have. Along with this, you can also specify an AMR budget, right? And that budget limits the total cell count of any run to whatever your discretion is. The Converge solver has a VOF-based option allowing for free surface and fluid structure interaction problems to be handled efficiently. Aside from the tremendous benefit of having the meshing fully coupled with the solver, also offers many discrete phase submodels and detailed chemistry with dynamic mechanism reduction. So we've tried to make running Converge in parallel as effortless as possible while still allowing for control. So Converge is automatically parallelized using the MPI technique with automatic load balancing. So what we found is that the 50,000 cells per core is a sweet spot for Converge. So this, for existing users, this can serve as a general rule of thumb when estimating how many processors a job will run on effectively. Converge also comes with a genetic design optimization tool this tool utilizes a genetic algorithm with merit and design constraints to effectively, I guess, think outside the box. This survival of the fittest approach achieves the best fit solution based upon the user's input and merit functions. So with all these features and Converge's ease of use, we are starting to see this shifting paradigm toward a more predictive CFD solution. And while Converge can achieve repeatable, highly smeared results, the tendency has been to move away from those and achieve a more accurate predictive state. So this means moving from lower order numerics to high order, and a fine mesh everywhere to mesh with grid convergence, meaning at what point for a given case does refining the mesh have a negligible effect on the accuracy of the results, and thus it's not worth the cost. So with all of this shift in paradigm, it's great, but what it does is it comes with a downside or a cost. And the cost in these types of analysis is the fact that they are computationally expensive. So along with the standard Converge and the free integrated Converge Lite within GT Power, we had room for Converge in the cloud. Converge in the cloud is a pay-per-use model that offers the solutions to new clients into CFD with a lower barrier of entry. And for existing clients, we'll be able to handle and manage their CFD workflow or overflow effectively. So this kind of concludes the overview of Converge. Now I'd like to hand off to Ilea Graedel, the Manager of New Business Development at Rescale, and her talk detailing the current and projected HPC and cloud environment for engineering applications. And then this will be followed by a brief case setup within the Converge studio, and then a walkthrough of Rescale's workflow from Mulyanto Poort, the Vice President of Engineering at Rescale. And with this, I'll hand it over to Ilea.
Thank you. Good morning. Thanks everyone for joining us today. My name is Ilea Graedel, as Rob said, and I'm the Business Development Manager at Rescale. And so I'm sure many of you have heard the word cloud recently. It's definitely something that gets thrown around a lot, but not all cloud services or providers are the same. So what I'll do is I'll be going over some of the trends in cloud computing and what to look for as you transition to using cloud resources for your engineering work. So cloud resources have been continually popping up in everyday life. Businesses use cloud resources for marketing and sales. Newsletters, magazines, books are all available in cloud form. We even get our news and weather through cloud sites, and more recently, sensitive information, including banking, medical documents, have found their way into secure cloud databases. So it's actually estimated that by 2017, cloud services will be a $250 billion business that spans almost every area of our personal and professional lives. Forbes highlights the NeoVise research report that states 74% of infrastructure as a service users currently access more than one type of cloud. So that can include public, private, and hybrid combinations of the two. These estimates and predictions do also include cloud use for engineering and science applications. In terms of engineering work, on the next slide, I'll be showing how high-performance computing is a frequently used resource. So HPC is a versatile compute type that has significant speed and performance improvements over standard servers. Because of this, HPC servers are commonly used by engineers, scientists, and researchers around the world to perform complex analyses. HPC clusters are most commonly found still internally at company facilities. However, there definitely are some challenges with purchasing and maintaining an in-house HPC cluster. One of those challenges is that HPC clusters are typically designed and purchased to handle the average base load for simulations. So not only can they take weeks or months to purchase, even once they're actually on site, HPC clusters have high operational costs, including an AIT team, cooling capabilities, and just sheer power usage. Since engineering and science simulations are often not constant, queues can quickly form as engineers are forced to wait for the available compute space. And even once hardware is available, it might not be the best configuration for a specific analysis. Because of some of these challenges with internal HPC clusters, trends and research have begun to pop up that demonstrate the increase in cloud HPC usage and its estimated predictions for future growth. HPC processor usage in general is on the rise, and Intel saw over a 12% increase in HPC revenue from 2012 to 2013. Cloud HPC usage specifically doubled over a 2-year period between 2011 and 2013, increasing from 13.8% of overall HPC use to 23.7%. Within about 5 years, it's actually estimated that cloud HPC resources will be roughly 45% of all HPC use, with about $22 billion spent each year on high-performance computing in the cloud. The American Society of Mechanical Engineers highlights that HPC cloud popularity really isn't that surprising, given that users can fully optimize engineering designs and study more detailed models than you could using internal clusters. Flexibility and scalability that's offered in the cloud, Admin Magazine points out that users can run simulations ranging from single runs to digital rendering to low latency, high throughput jobs. And engineering.com actually highlights the extra horsepower, in a sense, that is instantly available to engineers at an on-demand rate as one of the reasons cloud HPC has become so effective. High-performance computing capabilities in the cloud really allow engineers to fully customize hardware to each specific analysis. And since engineers then aren't limited to the number of processors they have internally, projects can quickly be scaled out to significantly reduce the convergence time. Users can instantly kick off as many jobs as they need, each with different hardware profiles and parameters. And because of the virtually infinite resources, engineers no longer have to queue up to wait to run their simulations. For cloud providers who also integrate software, licensing issues are then also eliminated. But one of the really nice things about HPC cloud resources is that they can be accessed from any computer in any location in the world. With simulation data in the cloud, collaboration with colleagues instantly becomes easier. Users can share files, results, job parameters instantly without having to manually transfer the data. But one of the most popular features of HPC cloud computing is that on-demand pay-per-use model. So most cloud providers have no upfront costs and no downloads, meaning that you can access additional compute power whenever and wherever you need it. And as popularity increases, the costs will decrease, making these complex engineering simulations more and more affordable. So all of these features are great, but it's also important to understand what simulations you can run with cloud HPC. Today, cloud engineering platforms can accommodate everything from a single run to a massive DOE to complex optimizations. But jobs best suited for running in the cloud are embarrassingly parallel analyses and simulations that are computationally intensive, including MPI jobs. Small input data simulations also run very well with cloud resources, just because data transfer times then are minimal. Because computationally intensive analyses are a good fit for cloud, computational fluid dynamic simulations are ideal. And with a push towards predictive CFD, as Rob mentioned earlier, cloud hardware scalability is becoming more and more important. Some other jobs that run well in the cloud include millions of element for finite element analysis simulations, molecular sequencing analyses, and even large reservoir mapping jobs for the oil and gas industry have been moving towards the cloud. So it really spans the entire range of industry verticals, everything from aerospace to automotive to energy to life sciences. But there definitely are some jobs that do not perform as well in the cloud. Simulations that don't run as well with cloud resources include low computational analyses and jobs with short runtimes, so those that would converge in less than 2 or 3 hours. Very large input data jobs are also sometimes not the best to run with Cloud HPC right now, just due to the uploading speeds. But this is in large part dependent on both the user and provider's bandwidth, so it can vary user to user and job to job. But with current configurations, these types of analyses are still best executed internally. There are several important factors to consider when looking to run engineering simulations in the cloud. One of the top considerations is security. When looking into HPC cloud services, there are a couple security questions you do want to make sure you ask of cloud providers. Data encryption is an important factor, so data should always be encrypted, whether it's at rest or in transit, and should be encrypted beginning on the user, or you'll hear it sometimes referred to as client side. Server or kernel encryption and data center security are in part interconnected in terms of asking questions of cloud providers. So data centers, whether they're owned directly by the cloud provider or as third-party facilities, should always work to ensure the confidentiality and isolation of user information. And one way to do this is through kernel encryption. So essentially, if a person were to physically remove the server, they should not be able to read any analysis or user information. Relating to data isolation, when engineers actually go to run their simulations in the cloud, it's important that data is completely isolated from other user information. So for all analyses, but especially highly confidential jobs, it's crucial that simulations are completely separated. And finally, you should ask cloud simulation services if they perform external audits and follow national security standards. So SOC 2 Type 2 is an external independent security audit that ensures the company meets or exceeds specific security standards. For certain defense and military jobs, you should also check to make sure that there is a separate ITAR platform apart from general users. Apart from security, ease of use is another major factor when deciding to run cloud simulations. If setting up a job in the cloud takes a significant amount of engineering time, then it can quickly outweigh the compute benefits gained by increased hardware performance. Learning a new system can also take time, so cloud providers should have a platform and interface that is very easy to use. One aspect maybe not as obvious is software company and cloud provider interaction. Since most simulations require commercial software, it's important to make sure that the cloud provider and the software vendor have a good partnership. Many HPC cloud resources are available on demand, but you should also check to see if simulation software licenses have on-demand options as well. So HPC cloud resources in general are on the rise and can definitely help in running a wide range of engineering and science simulations much faster than conventional resources. Not all analyses are the same, nor are cloud providers. So one of the best ways to determine if moving to the cloud will work for your simulation workload specifically is to find an HPC cloud provider and try it out. Some do offer trials, and it's a really easy way to try before you buy. So Rob, I'll turn it back over to you.
All right, thank you, Ilea. So now I guess we'll take a look at Converge in the cloud with our SI8 tutorial. Converge. Okay, so as you'll notice, I have the SI8 geometry imported. I'm sorry, the boundaries have been flagged, and the run parameters have been set up, as you can see by the green checkboxes in the case setup utility off to the right here. We also can click on our timing map and look at the open and closing of the exhaust and intake ports, as well as when our embedding is turned on, and when we have detailed chemistry and AMR is turned on. So what we want to do from here to run in the cloud is we want to export our input files. So it's as simple as file export. And we export the input files. We specify our directory we'd like to export them to, select the folder, also check the files that we would like to send out. And what we do is we hit OK and we send them out. So that's the prep work. Aside from setting the model up, that's really the prep work that you have to do in order to get it available, or get the input files available for Rescale. So from here, I'll hand over control to Mulyanto Poort, the Vice President of Engineering, and he's going to step through the Rescale workflow.
Okay, thank you, Rob. Hi, everyone. I'm Mulyanto Poort. I head up engineering here at Rescale. And I'm just going to walk you through a quick overview of how to run a Converge job on Rescale. And I have the SIA tutorial model saved here on my desktop in a folder. And so the first thing you might want to do is zip up all the files into a single zip file. This is not required, but it is a lot easier to only upload one file as opposed to a single zip file. As opposed to each file individually. So I'll call this file input, and I'll move it to the desktop so it's easier to find. And now we're ready to set up our job on the Rescale platform. And you can access the Rescale platform by opening any browser and going to platform.rescale.com. And so the first thing you will see when logging into Rescale is a list of your jobs that you have previously created. And it also lists all the jobs that have been shared with you. Right now we are interested in creating a new job. So I'm just going to click on the new job link here at the top. And this will bring us to the job setup page. The job setup happens on 2 pages, and this is the first page, is the setup page. And on this page, we essentially do 2 things. The first one is to select the analysis software that you want to use, and the second part is to configure your hardware and to customize it for the specific software that you've chosen to run on. So the first thing that I'll do is rename the job so it's easier for me to find later on, called Converge Demo Job. And then we're ready to select our software. And the easiest way to do that is to just start typing the name of the software that you want to use. And so we want to use Converge. And by selecting Converge, if you haven't set up a license server yet, you will be prompted to specify your license server. You can use your own license server by entering in the address of your license server, for example, 27,000 at your license server. Alternatively, there's also on-demand hourly pricing available from Rescale and Converge. You can request this licensing feature to be activated, and if it's activated for you, the second radio button will show up, and this will use the hourly on-demand licensing provided by Rescale. So for this job, we're going to use that feature, and so that's all we will have to do for setting up our license. And we'll click OK. So right now, you can see that we've selected Converge, and it shows up here on the right side. It shows that we're running version 2.1, and we're running MPI. You can toggle MPI on and off, but of course, since we want to run on multiple cores, we will leave that on. So now we're ready to customize our hardware, and that's done at the bottom here. We recommend running Converge on the HPC Plus core type because it has the best interconnect and in general has the best processor and overall hardware as well. To show you real quick how the hardware summary works on the right here. So if I specify, for example, 32 to run on 32 cores, you can see on the right-hand side that we're actually running on 2 nodes, and that each node has 60 gigabytes of RAM memory, as well as 640 gigabytes of SSD storage. So that comes up to a total of 120 gigabytes of RAM memory and 1.3 terabytes of storage for the entire cluster. Since the SI8 model only has about 500,000 cells for most of the runs, we don't quite need 32 cores to run it, so we'll just select 16. And as you can see, it has updated our hardware summary here. So that's all you need to do for selecting your analysis and hardware settings, and now we're ready to set up our workflow. And we can go to the next page where we do that. And so this is the workflow setup page. You can optionally specify a parallel process like a parameter sweep or a design of experiments, or an iterative process like a optimization. But since we're running only a single run job, we're not interested in that, and so we'll skip straight to the configuration down here. And the first thing we'll do is upload the file that we just created, and it's really easy. Just upload, click the upload button and select the input file that we created. And on the bottom right-hand side, you can see the progress of the upload so far, and you can see that it's a very small file, and that is one of the advantages of using Converge. So you don't have to upload a big mesh file, because it is the meshing while running the simulation. And so that's all you have to do to upload the files. So we've got our file uploaded, and it shows up here on the left-hand side. And so now we're ready to do our last step, and that is to specify the command to run on Rescale. And we've created a simple command where you only have to specify 2 values. The first one is the number of MPI ranks you want to run on. This is either a numerical value, like 16, because we selected 60 cores, but you can also just specify all, which will run on all the cores that are available. And in 99.9% of the case, you specifying all is sufficient here. And then the other value that you have to specify is version, which is 2.1. And then optionally, if you are running a special build locally or an old build locally, you can actually specify the build number that you're running locally. For example, March 7, 2014. It's just a six-digit build date. If you don't specify this, it'll just use the latest build available on Rescale. Optionally, you can also specify post-process commands. Converge does supply certain tools to do post-processing, but we are not doing this for this run. And so this is all you would have to do to set up a Converge job. So let me just real quickly recap the process of setting up the job. It's basically a 5-step process. First step is to name the job. Second step is to select your analysis software. The third step is to customize the hardware that you want to run the software on. The fourth step is to upload your input files. And the last step is to specify the command to run Converge. And so now we're ready to submit the job. And I'll just click on Submit here. And this will bring us to the status page. And so there's really quite a bit going on in the status page. So I'll just walk you real quickly through all the things displayed on this page. On the right side, you can see the general stage at which the job is. So we initially queued the job, but pretty much every time you can, it immediately gets submitted unless you decide to run it on a low priority queue, which is a low-cost feature available on Rescale. Then you validate your input, and then the first step is starting a cluster. And so right now we're basically starting a cluster. This will take anywhere between 2 to 10 minutes, but since we started up a fairly small 16-core one-node cluster, this will usually take no more than 3 or 4 minutes. On the left side, you've got a little bit more information. The big difference here is that you have the timestamp of when these events happen, so you can come back later and see when you, for example, started your job, and you can kind of calculate how long your job has been running. I'd like next direct your attention here to the top right hand corner, and there's 3 buttons here, and I'd like to go over 2 of the features here: the share feature and the clone feature. The clone feature I will talk about later, and now I would like to talk about the share feature. One of the nice things about sharing is that if you run into an issue with your job, or you need help with job, you can share your job with Rescale support, and you can do that by clicking on the share button, and then clicking on the share with support button here. And this will send an email to Rescale support notifying us that you have you've requested help with this particular job, and we will get back to you and open a support ticket for this specific job. Alternatively, you can share your job with anyone in your company or organization. And for example, I could share my job with Ilea by entering in her email address here. And clicking share. And this will send an email to Ilea with notifying her that I've shared this job with her. And it will also contain a link that she can click on, and it will bring her to exactly this status page of the job. Also, when you share a job with other people, they won't be able to edit or change anything on the job or job setup. They can only view whatever you are viewing, so they can mess around with your job. What they can do is make a copy of the job and then run the exact same job themselves. So in the meantime, our cluster has started up, and you can see that from that has a green check mark right next to the starting cluster stage, a spinner right next to the running job. And so now we can start to monitor our job by looking at the output files in the working directory. And so the way to do that is to select a run you want to monitor. In this case, we only have one run. So you click on the number 1 here, and it will display a list of all the files in your working directory. And you can filter these files using this box up here. And so we can, for example, look at all the log files. And you can see that we have a high-level Rescale log here, and this basically shows you the commands that you entered, the build number that you're running, and the version that you're running. And then we also have the Converge log, which has your your Converge standard out information in it. So you can see that we're at cycle 17 and like 439 degrees before top dead center at this point. You can also download the entire file to your drive by clicking the download button here on the right-hand side. Not only can you look at logs, you can basically look at any out file that Converge creates. So, for example, the cell count outs if you want to monitor load balancing. And now you can see we have approximately 500,000 cells. And we're ranging between 26,000 and 32,000 cells per core, which is pretty good load balance. And that's what you can do with this, this output file tailing feature. You can use this feature on your computer, but you can also use it on your mobile devices or iPads by just simply copying this URL into your mobile device, and so you can check your jobs on the go and monitor your output files on the go as well. And that's basically a short overview of the status page of your Rescale job. So I would next like to talk a little bit about cloning your job. Cloning is a feature where we basically just create an exact copy of your job setup into a new job. And this is useful if you want to create a fairly similar job, but don't want to go through the entire setup process of selecting your hardware and selecting your analysis code and so on. So to do that you can do that right from your status page here by clicking on clone. And this will bring you to the setup page of your new clone job. And you can see that all the information is automatically loaded for you. So it's automatically picked Converge. It has the same number of cores selected. But since we are averaging only, say, 30,000 cells per core on our previous job, and we're thinking that's too little, we could, for example, reduce the number of cores to run on here. So we're closer to the 50,000 suggested cores. We can then go on and rename our job. For example, call it 8 cores. And we can maybe change the build number that we run on. And then we're ready to submit the job. And so you can see that in 30 seconds you have an entirely new job up and running. And so that's the nice part of being able to clone a job. So that's a cloning feature. And lastly, I'd like to really quickly go over what happens when your job finishes. I ran this job earlier on, and so it has finished running on Rescale. So there's this job here, my jobs list called Converge Demo Job Finished. You just can click on that job, and it'll bring you to the results page of that job. And if we navigate back to the status page real quick, you can see that we've got green check marks next to every stage of the job, so we know it's finished. And then on the results page, you can see how long it took to run a job. So this one took 17 hours and 23 minutes to run. And then lastly, on the right hand side here, you can download your files. So you can either download all your files in a single zip file by clicking this button, or you can view a list of files by clicking the List button. And this will bring up a list of all the output files that Converge has created. So you can download individual files, but you can also just view individual files inside your web browser by clicking the View File button. And it'll just show up in the window here. And alternatively, you can download an individual files. For example, we can download the log file here. And lastly, last feature I want to show to you is downloading multiple files. So you can specify 2 or more files and click download check files as a zip. And that will zip up your files and download them as a zip file. So that's a short overview of downloading your files. And the last thing that we also support is a charge feature here at the top. But it's not very useful for a single run job. What the charge feature does is it charts different outputs across different runs. So if you have multiple runs, you can see how different output variables change for over different runs. But since you only ran one run, in this case, this charge feature is not enabled. And that concludes my short run-through of how to run a Converge job on Rescale. I hope I communicated how easy it is to set up a Converge job on Rescale, and we'll hope you try it out. You can sign up for a free account on Rescale, and we'll give you up to 100 hours of free demo time on Rescale. So I look forward to seeing you run on Rescale, and I'll turn it back to Rob.
All right, thank you, Mulyanto. Going to the final conclusion here. So that kind of concludes our cloud computing and workflow with Rescale webinar. I'd like to remind everyone that they can follow us for more information on our webinar series at convergecfd.com, also Facebook and LinkedIn. And likewise, you can follow Rescale at rescale.com or on LinkedIn. Myself, Ilea, and Mulyanto would again like to thank you all. It looks like we're running a little short on time, but should anyone have any questions, please feel free to contact either myself or Ilea, and we'd be happy to answer them for you. I hope everybody has a great rest of the day, and we'll see you again soon. Thank you.